The modern aircraft carrier stands as the ultimate manifestation of sovereign intent, a nuclear-powered industrial airfield designed to project kinetic force across every global meridian. At the heart of this immense projection lies a single, critical choke point: the catapult system responsible for accelerating a 50,000-pound payload to flight speed. The physics governing this moment are unforgiving, requiring this system to accelerate a massive dead weight to 150 knots in under 3 seconds. For 70 years, the United States Navy relied on the brutal efficiency of steam, a technology that is mechanically complex and thermodynamically violent by nature. In 2017, the strategic calculus of naval warfare shifted forever with the official introduction of the Electromagnetic Aircraft Launch System, or commonly known as EMALS. This transition sparked a fierce technological debate that reached the highest levels of the American presidency, questioning the very logic of modern naval innovation. Critics, including former President Trump, argued for the proven reliability of legacy steam, citing its impressive 99.5% operational uptime during combat operations. However, the decision to abandon steam was not a matter of mere preference. It was a cold response to the physical limits of the Nimitz-class. To understand the future of global naval warfare, one must first dissect the inherent limitations of the C-13 steam catapults currently serving the fleet. A steam launch is fundamentally a contained explosion, a sudden and uncontrolled release of high-pressure energy stored within massive, heavy-duty steel accumulators. Once the launch button is pressed, the system operates on a primitive open loop, meaning the energy release cannot be adjusted during the actual stroke. It is a purely ballistic event. If the initial calculation is wrong or wind conditions shift, the machinery possesses no internal mechanism to compensate. This lack of precision forces operators to apply a massive safety margin, deliberately overpowering the launch to ensure the aircraft clears the flight deck. The consequence is an excessive application of stress on the airframe, a violent physical jolt that significantly shortens the operational lifespan of the aircraft. Steam is a blunt instrument in a digital age, effectively a heavy sledgehammer used to launch the world's most delicate and precise avionics packages. Furthermore, the infrastructure required to generate this steam is a logistical nightmare consisting of miles of high-pressure piping running through the ship's bowels. This network of high-temperature pipes eats up critical internal volume, requires intensive manual maintenance, and introduces a critical vulnerability deep inside the vessel. The Nimitz-class carriers, powered by legacy A4W reactors, were designed in an era when propulsion was the primary consumer of the ship's energy. But the modern battlefield requires electricity, not just for screws, but for advanced sensors, directed energy weapons, and massive parallel computing arrays. This is where the Ford-class and its integrated EMALS architecture represents a total and irreversible break from 70 years of naval tradition. The Gerald R. Ford is powered by twin Bechtel A1B reactors, generating 3 times the total electrical capacity of the Nimitz's legacy power plants. This massive surplus of electrical power is not for speed. It is designed to transform the ship into a mobile, floating energy grid. EMALS utilizes this integrated grid to replace the sledgehammer of steam with the precise, programmable, and highly controlled curve of modern electromagnetism. Instead of a steam-driven piston, a linear induction motor creates a traveling magnetic wave that pulls the aircraft smoothly down the launch track. This system operates on a sophisticated closed loop, sampling the aircraft's speed 20,000 times per second during the 3-second launch sequence. If the aircraft accelerates too slowly, the system adds power instantly. If it accelerates too fast, it backs off to protect the airframe. This real-time capability eliminates the destructive steam jolt, drastically reducing peak forces on the airframe and extending the service life of the air wing. More importantly, it allows the carrier to launch a significantly wider operational envelope, from heavy strike fighters to lightweight, fragile surveillance drones. Steam catapults have an immutable minimum energy floor. They simply cannot dial down low enough to launch lightweight unmanned systems without destroying them. In a future battlefield defined by drone swarms and unmanned wingmen, an adherence to steam would render the carrier significantly less lethal. The strategic goal of this transition is the increase of the sortie generation rate, the speed at which the carrier can reload and relaunch magazines. The Nimitz-class sustains 120 sorties per day, while the Ford-class targets a sustained rate of 160. That is a 33% increase in sustained combat output, effectively adding a third of a carrier's worth of firepower to the fight. Yet, this transition has been plagued by the inherent friction of immature technology and the complexities of massive software integration failures. Early testing of the EMALS revealed a failure rate that was statistically unacceptable for the high-intensity requirements of near-peer combat operations. In 2015, a software glitch caused excessive vibration when launching aircraft with external fuel tanks, threatening immediate and severe structural damage. Unlike steam, where a fix requires a welding torch and dry dock, the EMALS issue was resolved with a rapid code update. This software-defined capability is the system's greatest strategic strength and simultaneously its most terrifying and modern operational liability. While steam pipes do not get computer bugs, they also cannot be upgraded over the air to handle entirely new aircraft types. The debate over reliability often ignores the critical nuance between operational availability and the raw frequency of mechanical failure rates. The Navy argues that while EMALS may fault more often, its modular nature allows for rapid digital resets, minimizing total deck downtime. Critics counter that, in a near-peer conflict, a system that requires a digital reset is a system that leaves the ship defenseless. Operational data from the FY23 test report showed one failure every 614 cycles, still far below the ultimate target. Despite these teething issues, the Navy's commitment to the EMALS architecture is absolute, driven by the physical layout of the Ford class. Reverting to steam is physically impossible. The Ford class lacks the massive boiler infrastructure and piping routes required to support legacy systems. The A1B reactors are optimized for high-voltage electricity, not the massive steam bleed required by the legacy catapult pistons of the past. To go back to steam would require gutting the ship's primary structures, redesigning the reactor interface, and accepting a far less capable platform. Global competitors have noted this shift. China's Type 003 carrier, the Fujian, bypassed the steam era entirely to adopt electromagnetic launch technology. This suggests a global military consensus. Steam is a technological dead end, and electromagnetism is the prerequisite for next-generation naval warfare. The argument, therefore, is not about which system works better today, but which system can survive the high-intensity wars of tomorrow. The strategic pivot toward electromagnetic launch is not merely a hardware upgrade, but a mandatory prerequisite for the Navy's ambitious air wing of the future. By the year 2040, the Pentagon mandates that 60% of all carrier-based aviation assets must be unmanned systems to maintain maritime air superiority. This massive shift from manned fighters to autonomous swarms fundamentally breaks the operational envelope that was established by legacy steam-powered catapult systems. Steam systems are essentially calibrated for high mass, and they struggle to impart low-energy launches without causing catastrophic damage to lightweight composite airframes. A typical steam launch initiates with a violent hydraulic water brake release, creating a massive transient shock known in aviation as the launch jolt. For a ruggedized F/A-18 Super Hornet, this 30G spike is manageable, but for a delicate surveillance drone, the force can be physically catastrophic. EMALS eliminates this inherent violence by applying a precise, linear acceleration curve that protects the structural integrity of the aircraft and its sensitive internal payload. This significant reduction in airframe stress is projected to extend the total service life of carrier-based aircraft by as much as 31%. However, the integration of this electromagnetic precision revealed unforeseen and dangerous interactions between the flight software and the underlying hardware physics of the system. In early trials, the high-fidelity sensors of the system detected the natural oscillation of external fuel tanks as a critical flight anomaly during the stroke. The computer, attempting to correct for this perceived wobble in real time, induced a resonance frequency that threatened to tear the aircraft apart on the track. Under a legacy steam architecture, this failure would have required a massive physical redesign of the fuel tanks or the physical catapult shuttle itself. With the EMALS architecture, engineers resolved the crisis simply by rewriting the control algorithm to ignore specific and identified vibration frequencies during launch. This adaptability proves the core thesis of the Ford class, that hardware is inherently fixed, but the potential of software is essentially infinite and adaptable. Yet, the reliability metrics of this software-defined system remain a point of fierce and constant contention within the upper echelons of naval command. A critical failure in a catapult system halts all flight operations immediately, effectively turning a projection platform into a giant, floating, and vulnerable target. The Navy's current reliability target is 4,166 cycles between failures, a standard that steam catapults have met for decades. EMALS is currently achieving one failure every 614 cycles, representing a reliability gap of nearly a full order of magnitude today. To mitigate this gap, the Navy has shifted its primary metric to operational availability, focusing on repair speed rather than the frequency of failures. A steam failure often involves ruptured high-pressure piping or valve seizures, requiring hours of dangerous cool-down and intensive hazardous manual labor for repairs. An EMALS fault is often purely electronic, allowing technicians to isolate and reset the specific module in a matter of minutes through a digital interface. This concept of graceful degradation allows the system to continue operating at a reduced capacity even when individual electromagnetic components fail during combat operations. Critics argue this shift is a form of statistical manipulation designed to mask the immaturity of a system that was rushed into active production. Nevertheless, the geopolitical momentum has already shifted away from steam, a fact validated by the recent and aggressive decisions of peer naval competitors. China's People's Liberation Army Navy skipped the steam era entirely, moving directly from simple ski jumps to the advanced electromagnetic launch system on the Fujian. The Type 003 Fujian utilizes a similar DC-based electromagnetic system, confirming the global trajectory and the technological future of modern naval aircraft launch. France and India are also actively evaluating the EMALS for their next-generation carriers to ensure seamless interoperability with the United States Navy's assets. The decision to adopt the EMALS is also a strategic decision about future energy management and the broader concept of the all-electric warship. Steam catapults are fundamentally parasitic. They bleed thermal energy directly from the reactor loop, which reduces the ship's overall thermal and propulsion efficiency. EMALS draws power from a shared electrical grid, buffered by massive flywheel energy storage systems that isolate the reactor from the launch pulse. This modern architecture frees up the reactor's thermal output for other high-energy applications, specifically for future directed energy weapons and advanced point defense. Future defense against hypersonic missiles and drone swarms will rely on megawatt-class lasers and high-power microwaves that require instantaneous and massive power pulses. These advanced weapons require electrical surges that a traditional steam-based energy architecture simply cannot provide without massive, inefficient auxiliary generator sets. Therefore, the catapult is no longer just a launcher. It has evolved into a critical power node within the ship's integrated energy management system. The physical constraints within the Ford class further cement this reality, as there is absolutely no internal space available to retrofit legacy steam equipment. The internal volume previously occupied by miles of steam piping is now dedicated to improved crew berthing and the advanced weapons elevator system. These advanced weapons elevators utilize similar linear motor technology to move ordnance to the flight deck faster than traditional legacy hydraulic lifts. Reverting to steam would require a total structural gutting of the vessel, representing a multi-billion-dollar error that the Navy simply cannot afford. Political rhetoric regarding a return to steam often ignores these immutable laws of modern naval architecture and the physics of nuclear engineering. The MQ-25 Stingray, a critical unmanned tanker drone, further complicates the argument for maintaining legacy steam systems on future aircraft carrier hulls. While the Stingray is heavy enough for steam launch, future generations of unmanned combat aerial vehicles will likely be much lighter and faster platforms. The versatility to launch a 10,000-pound drone immediately after a 60,000-pound strike fighter provides the ultimate tactical edge in a high-intensity conflict. Steam requires a slow, manual resetting of physical valves and counterweights to change the launch settings between these two vastly different aircraft types. EMALS changes these settings instantly via a simple touchscreen interface, significantly accelerating the flight deck cycle and the overall sortie generation rate. This speed is critical in a saturation attack scenario where every single second of flight deck inactivity represents a massive vulnerability to the ship. The ability to fine-tune launch velocity also significantly reduces the wind over deck requirements that have traditionally dictated a carrier's course for decades. Carriers often have to turn into the wind to generate sufficient lift for a steam launch, which dictates the ship's course to the enemy. EMALS can impart higher operational end speeds, allowing the carrier more freedom to maneuver while conducting flight operations in a contested maritime environment. This decoupling of launch mechanics from environmental conditions offers a subtle but vital tactical advantage in the age of long-range hypersonic missiles. The debate is ultimately settled by the requirements of the mission, not by a nostalgic preference for the mechanical reliability of the past. Political mandates attempting to force a return to legacy steam catapults effectively ignore the irreversible nature of modern naval architecture and advanced nuclear engineering. The USS Gerald R Ford is not a modular assembly that can be easily modified. Its hull and reactor plant were built specifically for electromagnetics. To retrofit legacy steam systems now would require cutting through 10 decks of reinforced naval steel and completely redesigning the entire nuclear reactor interface. The advanced Bechtel A1B reactors simply do not possess the high-pressure steam plumbing required to drive legacy catapult pistons at high combat operational tempos. Such a drastic reversal would cost billions of dollars in shipyard labor and sideline the world's most advanced carrier for several years of work. This multi-year delay would represent a massive strategic gift to global competitors, specifically Beijing, by removing a primary American deterrent from the Pacific theater. The heated debate, therefore, eventually collapses into a binary choice between the relative comfort of the past and the absolute necessity of the future. Steam remains comfortable to legacy operators because its failure modes are understood, but EMALS is necessary because its technological capabilities are essentially uncapped. Reliability data is steadily and measurably improving, with the latest operational tests showing that the system is reaching 98% total mission availability. This specific metric acknowledges a critical distinction. While the EMALS may fault occasionally, it does not remain broken for long periods like legacy systems. A steam failure is often a catastrophic industrial accident involving superheated vapor. By contrast, an EMALS failure is usually just a rapid server crash. Naval dominance in the 21st century will not be decided by who maintains the most reliable middle 20th century industrial technology in their fleet. Instead, it will be decided by who can launch the widest variety of autonomous systems with the highest sustained sortie generation rate during combat. The Ford-class is designed from the keel up to operate the air wing of 2050, not the legacy carrier air wings of the Cold War. This forward-looking architecture allows for the seamless integration of directed energy defenses designed to counter emerging and lethal drone swarm saturation attacks. A traditional steam-powered carrier cannot power a megawatt-class laser defense system without also installing massive and redundant auxiliary fuel-burning generators. The Ford's integrated power system, driven by the same logic as the EMALS, makes this energy available on demand for critical defensive weapon systems. Therefore, the current operational growing pains of electromagnetic launch are effectively the tuition fees required for future maritime supremacy and technological dominance. The modern aircraft carrier is no longer just a ship. It is now a central node in a hyper-connected and increasingly autonomous global kill chain. To downgrade the primary launcher back to steam would be to sever that chain and reduce the carrier to a simple floating airfield. The ultimate tactical advantage of the EMALS is the total decoupling of launch mechanics from environmental variables such as ambient wind speed and direction. By generating precise end speed regardless of the headwind, the carrier retains total tactical freedom of maneuver during its high-intensity flight deck operations. This allows the carrier's strike group to maintain a direct course toward the threat, rather than turning into the wind to facilitate a launch. In a modern battle space defined by hypersonic closing speeds, that freedom of navigation and maneuver is a vital trait for the ship's survival. The transition is admittedly painful, the costs are high, and the learning curve is steep, but there is simply no viable technological alternative. Global competitors clearly understand this underlying physics. They are building their future fleets to mirror the electromagnetic standards set by the Ford-class. The strategic question is no longer steam or electric, but rather adapt or obsolesce. In the face of increasingly capable near-peer maritime competition, as the United States Navy stares down a future defined by unmanned dominance, the engineering verdict regarding the Catapult system remains absolutely absolute. Steam technology belongs in a museum, preserved as a testament to the 20th century industrial might that once defined the American naval era. Electromagnetism belongs in the fight, serving as the kinetic engine for the next 100 years of sovereign naval power and global force projection. The silent, invisible pulse of the EMALS system is the true sound of a Navy preparing for a war it fully intends to win. Every successful launch cycle generates massive amounts of data, refining the complex algorithms that will eventually launch the sixth-generation fighters of tomorrow. The technical friction experienced today is the necessary foundation for the extreme lethality required for the difficult decades that lie ahead of us. There is no turning back to the age of steam. The only way out is straight through the current engineering and software integration challenge. The aircraft carrier remains the apex predator of the world's oceans, but only if it evolves significantly faster than its intended prey. EMALS is that necessary evolution, a leap across the technological chasm that separates the old Navy of the past from the new. While pundits continue to debate the reliability of the past, the engineers are currently coding the extreme lethality of the American future. The ability to launch a swarm of drones, recover them, and rearm in record time is the new global metric of naval power. That specific capability is exclusively the domain of the Electromagnetic Launch System and the integrated architecture of the all-electric naval ship. In the end, the carrier that can adapt its launch profile to any potential threat is the only carrier that survives the next conflict. The Ford-class was built to be that survivor, purposefully sacrificing short-term certainty for the long-term dominance of the global maritime commons. The Catapult has just one job, but how it performs that job effectively defines the entire combat strategy of the United States fleet. Steam pushes blindly with brute force. Electromagnetism pushes with intelligence, constant feedback, and an inherent ability for rapid, real-time adaptability. This digital intelligence is the margin of victory in a modern war where speed and precision are the only valid currencies of survival. The argument is finally over. The steam valves are permanently closed, and the massive capacitor banks are fully charged for the next launch. The future of naval aviation is silent, electric, and undeniably lethal to any adversary that attempts to challenge American maritime air superiority. Naval power is no longer measured in pressure per square inch, but in megawatts of power and the speed of processing cycles. The Ford-class stands as the physical manifestation of this new doctrine, a machine built for a new era of global competition. It is a weapon built not for the wars we have already fought, but for the wars we must deter through superior technology. Deterrence in the modern age is powered by the invisible force of electromagnetism, the current that will define the high seas forever.